Hello and welcome. Today we're going to talk about applications of analytic functions to fluid flow. So recall again what an analytic function is. An analytic function is, oops, we need to get a little bit bigger there. Oh, let's try a pen. There we go. F of z is equal to u plus iv, where we can rewrite this as f of x comma y is equal to u of x comma y plus I v x comma y. That's the more full way of saying it. And we know that if f is analytic in some domain D, so some subset of the complex plane, an open set, then we can write something like this. Then we know that u and v are harmonic functions. And another way we can put this is, of course, so this sort of puts perhaps the central attention on f of z being an analytic function. But we could also start again from the perspective of harmonic functions. We've already seen, and you've seen in the homework and other examples of where if we start with u of x comma y being a solution to Laplace's equation, we know this is it has many applications to fluid flow, which we're going to be talking about today, but also electrostatics and as well as steady state temperature distributions in conducting media. Okay, so if we start there, we know we can find V, which is the harmonic conjugate. And then from there we can construct f of z, which is analytic, which is going to be u plus iv. So here the information flows the other way. Start with u. If we have some u that solves an interesting real-world problem involving Laplace's equation right here, and then we can construct from u we can find v, and put them together and compose them in that fashion, and we have a f of z. So that's the other kind of way we can think about analytic functions, is sort of containing the information that starts with the Laplace equation solution, like so. Now the question is, so how do we interpret? So the big question then is how to interpret V given we have u. All right, so we have some function u. What does V mean? All right, if we've solved some applied problem involving electrostatics or fluid flow, so we have some function u. I can maybe come up with a graph of it. So the graph, of course, we're going to have, it's going to be maybe I'll write it like this, right? So here's some domain, and there's some surface over the top of it like that. That's in the x and y plane. So that surface, like so, that is u, right? So we can think of that vertical axis here being u of x comma y. We want to know then what v of x comma y, what information is stored in v. Given we know this u of x. Okay, so let's see if we can kind of address that issue. So let's first think about what we mean. So again, we have a solution u of x comma y, and we know that the Cauchy-Riemann equations, hold ux equals vy, and also uy equals negative vx. All right, so again, if we know u and we know its derivatives, we can find v through anti-differentiation. Okay, so there's no new information available in v. V is literally that conjugate. It's that extra sort of auxiliary piece of information that creates our analytic function. All right, so first of all, let's understand if u solves Laplace's equation. What that means is any I'll call it any domain. I'll call it M. So any domain M that's inside our big domain like that, I know the following is true. I know that the gradient field, U, dotted with the normal, dA, over this region is going to be 0. And this is, of course, the 0 net flux property. Okay, and we can write this as the divergence theorem, where we can now, sorry, this is over the boundary of M, all right, so the outer edge of M. Then we can integrate over M itself as the divergence theorem, which is precisely Laplace's equation. And because we can do this for any domain M, it implies then that this does hold. Okay, so in terms of fluid flow, if I think of the gradient field, so that I can write as Ux, Uy, right? I can think of that as a velocity field. Okay, it tells me where the fluid is flowing. And the zero net flux property says that we're in steady state. If I have some region M, right? That's my region M. And I want to talk about the fluid flowing through this region. I can draw out precisely this velocity field as a vector field. I'm drawing it as a bunch of arrows. And I know that whatever fluid is coming in one end, the other end has to it has to be coming out the other end at the same amount, and that is exactly that zero net flux property. So we're requiring that the fluid, everything's in an even flow, that there's no buildup of fluid within any region of space. That whatever's flowing in has to also flow out. Exactly how it happens, it could swirl around in there for a long time before it goes. But if you take a particle that's in this fluid, if it flows in at some boundary, at some point it's going to flow out. Okay. And that's precisely what the Laplace equation is saying about a fluid, where we usually describe the fluid by its velocity field. But you then, if we want to call it a field too, I would call that the potential field. Okay, so if we have the gradient field, which we'll call the velocity field of the fluid, and then U then represents that potential field, we know that a few things are true. First of all, if I think of my big domain here as I'm just going to write it like it's some big box here, right? And if I set U equal to a constant, I'm going to find all the level curves. So for instance, I can say U is equal to C, and there's some sort of set within the plane where U, so maybe we can start at, this is a low C value, and then as we go higher and higher here, we see, I'm just drawing this as a particular example, say, C is large. Okay, so that represents this potential, and then we know then, just from our understanding of calculus 3 material, that the gradient field has to be perpendicular. It's perpendicular to level curves. So we can write it as follows. We can always, the gradient field always has to be perpendicular to any level curves, and it will always point, if you will, uphill. It's pointing up to higher values of C, like so. Okay, and that's just one example I have written here. So that's one way to understand what U is telling us in terms of steady state fluid flow. Okay, all right, so with that example, let's now go to V. So if I have U, and then I have the velocity field, so that's Ux, Uy, but then I want to, so okay, what is V then? Well, of course, I can also write out V's velocity field, which I can write as Vx, Vy. So again, I'm going to draw that picture again I had before. this is going to be u. So this is this domain, and I'm going to write it like that as follows, just like before. These are the level curves, and I've just drawn this. This is just an artwork example. I haven't actually applied any equations here. And we know the gradient field of u looks like that. It's just going to be this. We depict it with arrows like so. Okay. All right. So the question is, if I draw it along here, if this is my u, what's my v look like? Okay, and what does it mean in relationship to this fluid flow that we have here? So we can think of this fluid as flowing kind of along this way, right? So let's use the Cauchy-Riemann equations. So here's the Cauchy-Riemann equations. We know that ux is equal to vy, okay? And we know that uy is equal to negative vx. So we put those into our gradient of v. We want to know what the gradient of v looks like. Well, we can write that as follows. We know then that wherever we see a vx, I can put a negative uy in its place, right? Wherever I see a vy, I can put a ux in its place. So again, v doesn't store any new information about our harmonic function. It's a direct result of u. So once I have u, I can find the gradient field of v, and I want to know what this represents, which way it points. And so how do I know, what directions? What's the relationship here? And it's pretty clear. We have a measure of angles I should say between any two vectors is the dot product. So I can always write, I shouldn't say v, I should use w. So if w is some vector in two-dimensional space, and maybe we'll call it w1, and then there's some w2, we know that's equal to, this is going to be, so if that's w11, w12, dotted with w1, or sorry, 2,1, w2, 2, all right? So these are the two entries of these two vectors here, and so on. We have a way of writing this as w11, w21 plus w12 times w22. Okay, so this is a real number, and this real number is always it's going to be if I take its absolute value, it's always going to be less than or equal to. Sorry, I should say this. It's equal to. I'm going to take away the absolute values there. This is going to be equal to the magnitude of W1 times the magnitude of W2 times the cosine of the angle between. So if this is W1 and that's W2, there's an angle between, and now we have the dot product is a measurement of the angle, and if theta is equal to pi over 2, which is 90 degrees, we know that the dot product is equal to 0. And that's, we can read that straight off. If I put a pi over 2 in there, we get 0. All right, so we have this nice measurement. So now let's check here. Let's look up here. Let's see what the relationship between these two vector fields are. So if I write the gradient field of u dotted with the gradient field of v, that's equal to ux, uy, dotted with, now we can put this in its place right here. We can put that right there as negative uy, comma, ux, and we see that that has to be uy negative plus uy times ux, which is clearly always 0. All right, so we can conclude then that ux is perpendicular or sorry, the gradient field of u is perpendicular to the gradient field of v. All right. And that also means because, and we can also imply because the gradient field of v is perpendicular to its level curves, it implies then that the level curves, I should say, of v are, I'm sorry, I'm running out of space here, are parallel to gradient of u. All right, so let's see if we can understand this a little bit. So that means then that the level curves of v are going to be parallel to here. So wherever I see this like nice little line, I can see this is sort of radiating like that. That will be a level curve. That is a point where v equals some constant. Likewise, if I see here's my gradient field there, I can see I can draw a line right there, and I'll draw like that. And they're sort of radiating out like that. So those are the level curves of v. And likewise, we know that its gradient field has to be perpendicular to its level curves, like so. So there we go. That's how we understand what's being stated here between these things. So now let's bring it back to fluid flow. So let's bring it back to fluid flow. So if u is the velocity field, the v's level curves are called the streamlines. So if I'm looking at my domain again here, and if I were to drop a little particle in this steady state fluid flow, and if I were to watch it travel over time, that would be a streamline. If I were to drop a particle in a different point, of course the streamline will be different. And those represent all the streamlines of our function. And of course, so again, these level curves they're parallel to the velocity field. So the velocity field is going to be flowing this way, and as a particle flows along that velocity field, it will draw out a streamline. So now we see this as f of z equals u plus iv. It's sort of a compact. Is a compact way to store a fluid flow solution. All right. So analytic functions are a way to represent steady state fluid flow in 2D. Okay. So let's go to an example really quick and then close out this video here. So let's talk about one of our most favorite functions, which is f of z squared. So this is an analytic function. Now let's see what fluid flow it represents. So we can write this as x plus I y squared, which is equal to x squared minus y squared. That's the real part. So that's our u plus I, and then we have a 2xy. And that represents our v. All right. So let's see. So let's find out what the gradient field is, what the velocity field for this solution looks like, and it's pretty clear to see that that's going to be 2x, and that's going to be 2y, or minus 2y, sorry. Okay, and we can go through the process. So I'm going to draw this really big, and I'm just going to draw it in the upper quadrant of our situation here. So this is going to be y, and that's going to be x right there. All right, and so and that'll say is 1. That'll say right here is 1 there, 2. And there's a 2, and then there's a 2. Okay, and at the point 1, 1, we see that it should be pointing down and to the right like that. Okay. Likewise, right here, it should be pointing down and to the right, but a little bit smaller. A little bit smaller. So anywhere along the 1, 1 line, like that, we see we have it pointing at downward at 45 degrees, but it gets bigger as it goes out. The vector gets bigger. Okay. Likewise, if I go here, let's say if I go to 1/2, and I stay at 1, now I'm going to go up to 2. So what do we see here is if I put 1/2 in here, I get a 1. So I go over 1 in positive direction, but I go down 4. So I have to think of a 1 to 4 relationship. I'm not drawing these vectors to scale, but rather you just have to make sure you get the aspect ratio about right. And the same thing here, if I go to 2 here and 1/2 in the y direction, I see there's the same symmetry there. Kind of looks like that. All right, so what we're seeing here is it kind of looks like this. There's kind of a curvy flow to it like that. But the vectors on the whole get bigger and bigger and bigger the further you get away from the origin. Around here, all the magnitudes of the velocity. So the velocity overall, the speed of the fluid is very small near the origin, and it seems to get bigger and bigger as you go further out. Okay, all right. So another way we can look at that now is look at the streamlines. So another way to represent the same information without having to go through finding all these little vectors. So that gives you the magnitude. Maybe you're more interested in the speed, so you might want to look at the magnitude of this. So I might want to look at the magnitude of the gradient. So this is the vector magnitude, which will just simply be 4. It'll be 2 square root of x squared plus y squared. So that's clearly going to be 2 times the modulus of z. So the fluid seems to be getting faster and faster and faster as you get further away from the origin by a factor of 2 times the distance from the origin. All right, so what about streamlines? They should give us maybe a more concrete picture of where particles flow in this system. So again, we set 2xy is equal to some constant. Okay, so we can try, let's make our constant equal to 2, for example. There's an example. Then you get, we want to get y, it must be equal to then 1 over x. All right, so there is a streamline to our function. So it should be going through this point, and it'll kind of go down. So maybe what I'll do is actually we can, I'm going to get a slightly different color here, just so we can be really cool. So the streamline will be a 1 over x type behavior, okay? Like that. And likewise, we'll see now if c is a different value, say, call it 4, then of course you're going to get a y is equal to 2 over x, right? And so that will be, so if x is equal to 1, then y is equal to 2. So that'll be up there. And it should go like that. And they should meet up there. As you go further up, these should connect up together, get closer and closer. So you see the fluid flow lines look like these 1 over x type lines. They're all proportional to 1. Oops. They're all proportional to 1 over x. So we see now that analytic functions have a lot of information when it comes to fluid flow, and they store it in 2 different nice compact packages, right? So now we have a really interesting phenomenon where we can use analytic functions as a way to represent information about fluid flow. So thank you very much.